All right, in this lecture, let's talk a little bit more in detail about the Quark model and the structure of hadrons. So recall that we were motivated in the introduction and by the conservation laws that the conserved properties like strangeness, charm, beauty can be explained in terms of new fundamental particles that carry that quantum number, namely the so-called quarks. Now, where did this come from? In 1964, physicist Murray Gell-Mann, as well as George Zweig, proposed a theory for the apparent structure in the particle multiplets that help explain the particle zoo, so to speak. There was such a wide proliferation of particles, but you could really explain it by these few fundamental components. And this is known as the Quark model. Now let's go over this model and how we can build hadrons, that is particles containing quarks, in this model. So baryons, which are the fermion particles, the spin half integer spin 1/2, 3/2, and so on, are comprised of 3 quarks. Now, you can choose any 3, but a baryon is a bound state of 3 quarks. The mesons, which have half integer spin, so like spin 0 or spin 1 in units of h bar, are bound states of a quark and an anti-quark. So you can pick any one of these quarks and combine it with any one of the anti-quarks. However, there is one caveat. Actually, in practice, you cannot add the last quark, the top quark. It's because of its extreme mass, it decays very promptly, too promptly to form a bound state, or so we think. But okay, let's see how this works out. So let's discuss baryons. And let's start with the first 3 quarks, or the lowest mass quarks, if you like. And that is the up, down, and strange quark. The up quark has an electric charge that is plus 2/3 times E, and the down and strange quarks are identical in terms of electric charge. They have minus 1/3 E. Now, it turns out you can arrange baryons into these so-called multiplets. They form patterns like shown here. The axes don't matter too much, but this, as we'll see, they'll be related to the electric charge and something called isospin. But basically, we're going to organize these in terms of charge and mass. So let's see how this can work. Let's start with the particles you're familiar with, right? The neutron and the proton. Now we are told that to make a baryon, we need to combine 3 quarks. So let's see how we can combine them to make a neutron or proton. Let's start with the proton, right? It has a charge of plus 1 unit of E. So I could start with an up quark, right? That's 2/3. I can add another up quark. That's 4/3. Oops, I've overshot. I need plus 1, not plus 1 1/3. But I can add a down type quark, which has a charge minus 1/3, and come out okay. So I add a down quark. So the proton in this quark model is comprised of 2 up quarks and a down quark. How about the neutron? I need to come out electrically neutral, right? Well, what if we replace one of the up quarks with a down quark? In other words, what if it is up, down, down? In that case, I have up, which is charged 2/3, and then I'm subtracting off 2 down quarks, which each have charge minus 1/3, and indeed I am neutral. Okay. What about these other particles in this diagram? The sigma baryons, even the lambda baryon, as well as the Xc baryons. Well, one thing that characterizes these baryons is as I move down from above to below, the mass is increasing. So mass increases downward. And which particle is heavier than the others? And that would be the strange quark. A strange quark is a bit heavier. So what if we replace a down quark, which has charge minus 1/3 e, with a strange quark, which also has charge minus 1/3 e? For example, what if we started with the neutron? It was neutral. If I just replace one of the down quarks with a strange quark, it also should be electrically neutral. So in other words, the sigma 0 and the lambda 0 could be written as UDS. 2/3 in electric charge for U, and then minus 1/3 for the down and strange. What about sigma plus? Well, I need to add more charge. It's more like the proton. So in that case, we can just replace the last down quark in the proton with a strange quark and have up, up, strange. Okay. And sigma minus, well, in that case, I want to keep the 2 down quarks and change the up into a down type quark, meaning a strange quark, to come with charge minus E. So this would be basically D, D, S. And that would make a sigma minus baryon. Now, one thing to note here is if we're talking about the strangeness, the neutron proton were not strange particles, so they have strangeness equal to 0. But the sigma baryons and lambda baryons are strange particles. They carry strangeness, and the strange quark effectively carries minus 1 unit of strangeness. Okay, and that would meet the convention for the strangeness of those sigma baryons. What about the last bottom row, the Xc baryons? Well, by just following the trend, that's most likely going to be 2 units of strangeness, minus 2 for the strangeness. It's heavier in mass, but the strange quark is heavier. So adding 2 of them must make a heavier mass, right, than the say, adding just 1 or 0 strange baryon. And so let's see what comprises that. I have a sigma, sorry, not sigma, a Xi minus for the bottom left part. And I need to add 1 more strange quark, but I can just flip one of the down quarks into a strange quark, right? So I could write this as D, D, S. And that would make the Xi minus. What about the Xi 0? Again, I can change a down type quark into a strange quark, and I could get USS. And so you can see how I can write now the composition of these hadrons, these baryons, in terms of this quark model of combining 3 quarks. But I have to make sure to obey that the electric charge matches what I need, and then the more strange quarks I have, the strangeness increases, the mass increases. One thing you'll also be able to note is there is indeed, as I advertised, a relationship between the charge in this plane, right? The middle row here, middle diagonal, I should say, has charge 0. The proton and sigma plus have charge +1, and the sigma minus and Xc minus have charge -1. So we can see that along the diagonal axis, charge is increasing up and to the right. Okay. But those are not the only baryons. Actually, there's plenty of them. So let's bring another row. And what is different about these baryons than the ones we just discussed? That has to do with the spin. So originally, for the first multiplet, I didn't say, but we were dealing with spin 1/2 baryons. But you can also have a half integer particle, but have it be spin 3/2. Think of it as in a more excited state because it has more intrinsic angular momentum, or angular momentum in general. And you can see in this diagram that I've just brought up, there's a lot more particles showing up there. So again, how can I make these particles from these 3 quarks that I've listed here? Let's start with the top row, the delta baryons. And maybe I take the extreme left and the extreme right. The extreme left is a particle delta minus, which has a charge of -1 unit of E. And clearly, if this is the lightest of this family of particles, I shouldn't add a strange quark, so it probably means all down quarks. Down, 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 right? -1/3, -1/3, -1/3 gives me -1 unit of E. Likewise, the far right side, the delta plus plus, would be up, up, up. 2/3, 2/3, and 2/3 gives me 6/3, which is 2 units of electric charge at E. And you basically, in between for the delta 0 and the delta plus, are start replacing some of the d quarks with u quarks, right? So I could have du or duu. And then that should give me the appropriate charge in that case. Now, for the next row, I'm reaching strangeness -1. That's the sigma baryons, but not the same sigma baryons. So there's a little star there. It just means an excited state, sigma star baryons. And now I need to replace a down quark with a strange type quark in that case. And that should essentially do the trick there. So I could have down, down, strange for the sigma star minus, and the sigma star plus. Well, let's just go ahead and replace these. I could have up, up, strange for the sigma star plus, 2/3, 2/3, 4/3, minus a third is +1. And in between, I would just have UDS here. Those are the only combinations where I have just one strange quark in strangeness -1. Now, the next row is strangeness -2. So I need 2 strange quarks for 2 units of strangeness, but that's it. So I can have 2 strange quarks with either an up or a down quark, right? So if I do the down quark, I'm going to have DSS, and that'll be a charge of -1. Or I could add the up quark and add SS, and that'll be neutral, right? And then finally, well, it's not written here, but there's another particle, another row, with a question mark, by the way, which was strangeness -3. And the only combination of 3 strange quarks is 3 strange quarks, SSS. Why the question mark there? Well, back in the day with Murray-Gell-Mann, that particle hadn't been discovered yet. But you could see from this multiplet on the right here, going from 4 particles to 3 particles to 2 particles, you can see a trend. You could predict that, there must be yet a heavier one with only 1 particle. And so they in fact predicted that particle, even its approximate mass based on the mass difference from one row to the next. And they predicted the omega minus, and it was discovered. So very much a success of this Quark model. Okay, that was the baryons, where you combine 3 quarks. Let's talk about the mesons. Now, a meson is a bound state of a quark and an antiquark, right? And so they're integer spin, not half integer spin. And here I list that, of course, the up-type quark has charge +2/3 e, the down type or strange type -1/3 e, but the antiquarks have the negative of that charge. So -2/3 e for the anti-up, and +1/3 e for the down and strange. Okay, let's look at a multiplet of mesons. Let's start with the scalar mesons, which means that the spin was 0 in this case. So I have kind of a different pattern here, and actually it won't follow the pattern I had before where the mass was increasing downward. It actually will start from the middle row and will increase a strange quark or an anti-strange quark going up or down. So let's start from the middle row, and let's start with the pion family, pi minus, pi 0, pi plus, and see how we can make that from a quark and an anti-quark. So for example, the pi minus, it's negatively charged. So I'm probably going to need a down type quark. And what if I added an anti-up? -1/3 for the electric charge of the down type quark, -2/3 for the anti-up quark, -1, that works out. The antiparticle of that would be the pi plus, so that would be an up type quark and an anti-down, 2/3 plus a plus 1/3 is plus 1. And the pi 0, well, you have several options, right? I could just, to make a neutral, I could write up, up bar, but I could also write down, down bar, and you'd be right in either case. So which is it? Ah, that's where quantum mechanics comes in. It is a superposition of both of those states. The pi 0 is a superposition of a UU bar state, so up plus anti-up, and a composition of down and anti-down. All right. Now, going from that middle row, we can add a strange quark, so it'll be heavier, but it's heavier going both up and down. So for the kaon, the K0, the top left particle here, top left, that's going to be strangeness plus 1. The middle row, of course, was strangeness 0. And the K0 is strangeness plus 1. And turns out that is a down and an anti-S quark, because we saw that adding an S quark itself, a strange quark, at a strangeness of minus 1. So an anti-strange would have a strangeness of plus 1. Let's see if the charge works out. I have minus 1/3 for the down type quark. An anti-S quark has plus 1/3, so indeed it is neutral. And what about the K plus? Well, let's change the down type quark to an up type quark, add an anti-strange. So minus 2/3, and then I'm going to have a plus, well, hold on, let's see here. For the up type quark, sorry, it's 2/3 E, not minus 2/3. And the anti-S would be plus 1/3, so 2/3 plus 1/3 is plus 1, so it's a K plus. The bottom row are the antiparticles of the top row. So I have a K0 bar, for example, in the bottom right. And so I just take the antis of those, if you like, a strange quark and an anti-down type quark. This would give me strangeness minus 1, because remember, a strange quark had a negative 1 unit of strangeness. And that has charge minus 1/3, have an anti-down, be plus 1/3, so it indeed is neutral. And the K minus would be, therefore, a anti-up and a strange quark. And that should give you the minus charge. So that's how you do the scalar mesons, those mesons that have a spin 0. And one thing to note is that the K0 really is not identical to the anti-K0, the K0 bar. The difference is one has plus 1 unit of strangeness, so it has an anti-strange quark. In the other case, it has minus 1 unit of strangeness, and it has a strange quark. So they're not the same composition, even though they're both neutral, and we've labeled them with K0, but they're different particles. Finally, we can bring some more mesons. These would be the vector mesons. What does that mean? That means spin, and I've overused S here. I know it's not a strange quark. This is spin equals 1. So let me just write this here, spin. This was spin. And here we have excited states of the particles to the left, essentially here. And their composition would be quite similar to the ones on the left. The only difference is, for example, we have this phi meson here in the center, and that is actually a pure bound state of strange and anti-strange. So it doesn't have any strangeness, because one case has strangeness minus 1, the anti-S has strangeness plus 1, that adds to 0, so it goes in the middle row. But, and it is therefore more heavy because it has 2 strange quarks, one is anti-strange, but it's in that row where it had no strangeness. So a little bit different there. Okay, so this was an example showing you how to construct the mesons and the baryons from the first 3 quarks in the standard model of particle physics. However, there were more quarks, right? What about those? What about the charmed mesons and baryons, for example? And then there's also bottom mesons and baryons. But let's just concentrate on the charmed ones for now. Now my two-dimensional multiplets become more three-dimensional geometric shapes, okay? And we can do it for the mesons on the left. So this left side here are the mesons. And we could also do it for the right, which are the baryons. So we'll put the baryons in, and they're on the right. Remember, for the baryons, it's 3 quarks. And for the mesons, it is a quark and an antiquark, right? And let's start, say, from the right side with the baryons. And let me focus your attention to the bottom plane of this three-dimensional figure. That bottom plane, notice there's the neutron, the proton, the sigma baryons, and the Xc baryons, right? So that's that two-dimensional multiplet, but now kind of flattened out like a pancake in 3 dimensions there. And now what we're doing is we're essentially adding charmness going up. And that's the axis that's also drawn here. Charm is going up. Well, let's draw that a little neater. So we can start to replace some of the quarks in the bottom plane here with a charm quark. So you can see, for example, there is a neutral baryon called the sigma 0 with a subscript C, sigma C0, which is neutral. So I can do that with one up-type quark, but instead of using up, let's replace it with charm, which also is charged 2/3, like the up quark. And then subtract off 2 d quarks, so -1/3, -1/3 makes it neutral. But now I've added charm. And in fact, by adding charm, the mass goes up as well. So I can see I can replace up or down quarks with charm to fill this shape in the middle plane here with 1 charm quark. Or I can add 2 charm quarks, and then I have just up, down, and strange to replace it with. So if I just take 2 charm quarks with up and down, I can either add it with an up or I can add it with a down. That gives me the Xc plus Cc, or the Xc plus plus Cc, which means 2 charm quarks, one's positively charged, one's doubly positively charged, depending whether I had a down quark or an up quark. Kind of like that delta plus plus, but now I've replaced 2 of the up quarks with charm quarks. Anyway, so that's in that plane there were excited states down below. In that plane, here's those delta baryons, for example. There's that delta plus plus, but again, I can add charm or double charm, or even, as we see, 3 charm quarks, which make a doubly charged particle there. The difference from the bottom figure and the top figure is the spin of the baryon. Its bottom is spin 3/2, top is spin 1/2. Likewise, on the left were the mesons. And so the middle plane here, which should be familiar from just before, we did the kaons, the pions, and then the antis of them are at the bottom. So there's K0, here's K0 bar with the down, up, and strange quark and antiquarks. I can start to replace going upward. I can replace one of the up and downs, sorry, basically one of the up and downs or stranges with a charm quark. And D0 turns to be a meson with a charm quark and an anti-up quark. So it's neutral, 2/3 -1/3 for the -2/3 comes from the anti-up. Or D plus, where it's 2/3 plus another third gives me a plus. Or D sub S minus, where I've now added a strange quark in there as well. Or I can go downward and now I'm adding an anti-charm to a regular light flavored quark. So I hope you get the idea here. You can construct all these particles, but the general rules are for baryons, it's 3 quarks. You choose your 3. And for the mesons, it's a quark and an antiquark. But along with up, down, and strange, I also have charm and bottom I can add. Top, we don't, because it's very short-lived. This information, by the way, for these figures was drawn from the website from the particle data group, pdg.lbl.gov. Okay, that ends this lecture on the quark content of the hadrons.